Hello, my name is Caitlin McMillan, and in this video today we are going to derive the velocity distribution, the pressure distribution, the shear stress tensors, and the normal and tangential forces on a fluid creeping around a sphere. So let's get started. Hey guys, today we're going to solve for the velocity distribution of flow creeping around a sphere, and we're going to assume that it's steady and that we have a low Reynolds number significantly less than 1. And because of this, we can use this equation that I'm outlining here on this chart from the textbook, especially the one in green. It's very complex, but because of the conditions I said before, we can significantly simplify this equation so that essentially the whole left side cancels. And the equation can be simplified to 0 equals E4 squared. But keep in mind the boundary conditions in the box to the left of the green and the E squared to the box on the right, because we will be using that for calculating the boundary conditions. So we have 3 boundary conditions because this has a radial and a theta component and a psi component. And they're all dependent on each other. So from the table, we know that the radial component of the velocity equals this. And all of these are going to be solved at little r equals big R, because it equals 0 at that point because the sphere is not moving. And that makes the solving significantly easier because it's 0 for both the radial and it's 0 for all the boundary components. All right, now we're doing the velocity with respect to theta. Now we have a third boundary condition, psi, and this is as r goes towards infinity, and it's kind of as how the flow gets infinitely far away from the sphere and how it will behave. Now we have to solve for psi because it's dependent, or our radial and our theta components are dependent on it. So a solution must be postulated. We know it has a radial component, sine squared of theta, also a radial or an angular component. And it also has a radial component, and for this equation, we're just going to assign it some arbitrary FR value. And now we have to plug it into that E equation, which is based off the Navier-Stokes equation, but this is for spherical coordinates. And to make the math easier, we're going to solve it as E squared psi equals 0. And the E squared equation, again, is from the table, but here it is once more. Now this FR sine of theta, to help simplify this equation to make it easier to solve, we must distribute it throughout each of the terms. And we have to remember that when we do partials and long equations, we solve the partials from left to right. So here are some of the steps to solve the equation. as you can see, we're adding a partial of the radial component and a partial of the theta component. And that means we can convert it into an actual full derivative. And now we can factor out the sine squared of theta to get the first part of the equation. But we have to remember that this is only e squared times psi, so we have to multiply it, what we have just gotten, by e squared to get e for psi. And here's some of the steps for that. And when you simplify it down, this is what you get. And this is an equidimensional equation that has the same units throughout. So now we have to solve for CRN to help continue solve for psi. So we're going to plug it in to our equation. There's a lot of tedious math through this and power law rules. So those steps have been skipped for this video, and this is what the math will simplify down to. And we will get 4 constant values, or we'll get 4 exponential values that we will use to help solve for psi. Our n values, our exponential values, are going to be 4, 2, 1, and -1. And because there's no R4 in the psi equation, and it's higher than the highest degree in that equation, it's just going to go to 0. And in our psi equation, we know that it equals -1/2 v infinity r squared, and we have an r squared, so that means it equals C3, or C3 equals -1/2 v infinity r squared. And because there isn't an r1 or r to the -1 and r in the psi equation, but their degrees are lower than the highest degree, so we have to solve for those constants. And so now we have 2 unknowns and we need 2 equations. But if you remember, these partials are, the partial of this equation is required for the VR, or the velocity in the radial component, and the velocity in the theta component. So we're going to plug it into those equations and solve a system. Here is the steps for that. Here is the partial derivative of psi with respect to theta. And now we're going to take this partial and plug it in for velocity with respect to the radial component. And that simplifies down to this. And now we're going to do the same thing again, but for the velocity and the theta component. But for this one, we have to derive with respect to r. So here are the steps for that. Oh, actually, we can simplify VR by one more step. And this is a simplification of VR that'll make it easier to solve the system. Now we have to find, or we have to put the constants into the velocity with respect to theta equation. As I said before, we need to derive psi with respect to r. So here's some of the steps for that. Now we can plug this derivative back into the velocity with respect to theta, and this is what we get. And this simplifies down to this. And now you have two equations and two unknowns, so you can solve for C1 and C2. It helps to remember that VR equals 0, V theta component equals 0, and little r equals big R because we have a no-slip boundary condition. And when you solve the system, you get for C1, you get a negative 1/4 V infinity R cubed. And for C2, you'll get 3/4 V infinity R. And now you can take these values and plug them in for VR and V theta, and you'll get your boundary conditions. So here's VR, V infinity, parentheses 1 minus 3/2 times big R divided by little r plus 1/2 big R divided by little r cubed times cosine of theta. And for V theta, you get negative V infinity 1 minus 3/4 big R divided by little r minus 1/4 big R divided by little r cubed times sine of theta. And we have a third boundary condition, velocity dependent on phi, but because we are using the spiritual coordinate of the Navier-Stokes equation from the table, we assume that there is no dependence on phi. That equals 0. And those are the velocity distributions. Now we have to find the pressure derivation, and to do that we substitute it in the Navier-Stokes equation from B-7 and reach the spherical one, and we're going to substitute in the velocity of the radial component and the velocity of the theta component that we just solved for. And it's a very tedious equation, so it just simplifies down to this. And we get these two equations. And all you have to do now is to integrate the equations using the boundary condition as little r goes to infinity and pressure tends, or big P tends to P naught. And that will simplify down to the pressure equation. We're not going to show the integration because it's very tedious, but you would integrate this equation and the one above it, and this is what you would get. P equals P naught minus rho gz minus 3/2 times mu v infinity over big R times big R over little r squared times cosine of theta. And that is the pressure derivation for a sphere, flow creeping on a sphere. Now we are going to solve the stress tensors. And we really need tau RR, and you can get this from table B-1, what these equal. But important relation to know is that tau RR actually goes to the negative of tau psi psi, or negative 2 tau psi psi. And with negative tau psi psi, or phi, not psi psi, phi, it's this one right here, you don't actually have to derive anything because we can cancel out this side due to the fluid having constant density, and our velocity in the phi direction equals 0, so the derivative of that is just 0. So here are the steps to simplify down the stress tensor, the first stress tensor. And again, no derivation added. You really just have to add the velocity with respect to the radius plus the velocity with respect to theta times the cotangent of theta divided by r. And now that they've been added, there's just a lot of simplification steps. As you can see, the ones cancel, and we have like terms, so we can add them together. And we're going to try to get the big R over little r's to be by themselves. So we can simplify it as such. And to get it into our school, or to get it simplified down further so that you have a big R on the bottom, you can do this. And while this does equal tau psi psi, we need it to be equal tau RR. And to do that, we just multiply tau phi phi, I meant this is tau phi phi, by -2, which will give us 3 mu v infinity over big R times the negative of big R divided by little r squared plus r over little r to the 4th. And that is our first stress tensor. Now we have to solve for the stress tensor with respect to the the theta. And this one, there's only one option. So we know that tau r theta equals tau theta r, and it's this one right here. And this one we do have to take partials. So here are some of the steps, though the math is very tedious, but here we go. Though we are definitely going to skip steps for this one. But here are the partials that you would plug in to solve this equation. And this one, because we have to take the quotient rule. So this one is a lot more complicated. And when you plug those two derivatives into that tau theta r, or tau r theta, this is what your stress tensor becomes. And now you have the two stress tensors you need to calculate the shear stress tensors to help calculate the normal and tangential forces acting on the sphere. So now we are going to calculate the normal forces. And the resultant flow will be in the z direction, and the force can be obtained by integrating the z component of normal and tangential forces over the spherical surface. And we know that normal stresses are non-zero except at r equals r. So this is our z component, and we're going to multiply it by r squared sine theta d phi, and we need to integrate it. So our normal force will equal the integration from 0 to 2 pi, 0 pi of negative p plus the shear stress tensor RR at r equals r cosine theta sine theta d phi. The normal stress tensor can be eliminated, and what you are left with is p r equals p naught minus rho g r cosine theta minus 3 over 2 mu v infinity big R divided by big R cosine theta. And when you substitute this to the integral and solve it, you get your normal force equals 4 over 3 pi r big R cubed rho g plus 2 pi mu big R times v theta. And this one is this first one is your buoyant force, and the second one is your drag force. Now we need to calculate the forces tangential. At each point in the sphere, there's also shear stress tangentially. The z component of this force is tau little r theta at little r equals big R sine theta multiplied by the surface element r squared sine theta d phi. So very similar to the last problem, we are going to have to take an integral and substitute the shear stress in. So this is the integral that we will be integrating. And we calculated the shear distribution early in the video, but here it is again. And that is the tau r theta at little r equals big R is equal to 3 over 2 mu v infinity over big R times sine of theta. Now we have to substitute this into the integral and solve. And we will not show those steps, but when you solve it, you get force tangentially equals 4 pi mu big R times v infinity. And to get the total force, you have to add the normal to the tangential, which will equal 4 over 3 pi r cubed rho g plus 2 pi mu big R v infinity plus 4 pi mu r v infinity. And this first one again is your buoyant force. This one is your form drag force. And the last one that we just calculated is your friction drag force. And that is how you calculate the forces along a sphere when there's a fluid creeping. Thank you for watching. I hope that you learned something.